Hello everyone, it's my pleasure to welcome you all at the Hydrology and Terrestrial Ecosystems Model Techniques session of the GWF 2022 Annual Open Science Meeting. My name is Mohammed Ahmed. I'm a postdoctoral associate at the University of Calgary, and I'm currently leading and working on a couple of GWF sub-projects. For this session, we will have 6 oral presentations and 9 lightning talks. Due to the limited time, there will be no time for questions or discussion. Therefore, questions should be sent directly to the presenters. And for the presenters, please share your contact information in the chat so that people can reach out to you to ask questions, of course, if you prefer to. Lastly, we have a dedicated poster session on Wednesday so that you can explore the posters and join the discussion via chat rooms. Please check the program for more details. So for our presentation today and for this session, the first presentation will be given by Julie May, and the presentation title is the Great Lakes Runoff Intercomparison Project, GREP-GL. So Julie, the floor is yours.
Thanks, Mohammed. I hope you can see my screen now.
Yes, I can see.
Awesome. Perfect. Thank you so much. Thanks for the introduction. My contact information is on the bottom of all of my slides. So in case you want to contact me by email or on Twitter, that's probably the 2 best ways to contact me. I'm going to talk about the Great Lakes Runoff Intercomparison Project Phase 4. So there have been 3 before, and that's the 4th. And it's over the entire Great Lakes domain. It's the work of a large group of people that came together to set up their models over this domain. So let me I cannot advance my slides here. So as I said, there have been 3 projects before. One was for Lake Michigan, one for Lake Ontario, and then we started with Lake Erie. And when we were done with that one, we decided that we would now target the entire domain instead of moving on to the next lake, basically. So I'm going to present the highlights of that project here. The summary of this project is already under discussion in HES. You can find it there. The preprint is there with all the detailed results. I will really only highlight everything. So what we did is we set up 13 models where 1 is a data-driven model and 12 are traditional hydrologic and land surface models. 6 of those 13 models are set up in a lumped mode, while the other 7 are semi-distributed. 7 of the models are locally calibrated. So for each individual gauge station, 5 of them are regionally calibrated. So that means there is a model set up for each of the lakes. So 1 for Lake Erie, 1 for Lake Ontario, and so on. And 1 model has a global setup. So for the entire 1 million square kilometer domain, there's 1 model setup, and that global model is the data-driven model. So we used all the same forcing data set. That's RDRS version 2, which is an 18-year, 10-kilometer resolved forcing data set that basically contains all the variables that you would need to set up a hydrologic or land surface model. And besides that, we are also using all the same geophysical data sets. So we agreed on that data set after we finished with GREP-E. We were all sitting together and deciding which soil database, which land cover database, and so on to take. All models are also went out of their way and using the same routing product, except 1 model that is using the native one, but all other semi-distributed models are using the same. We are using the same set of stream flow gauge stations for calibration and validation. Only those stations were allowed for calibration, nothing else. And after we were done with streamflow, we are also looking at additional variables for evaluation. So the models are not calibrated against those additional variables, but we evaluate them after the fact, basically. So the stations we selected for calibration, there's 141, which we took care that they are nicely distributed across the entire 1 million square kilometers. But we also saved 71 validation stations that nobody actually knew about except Hongren and I, that we revealed after everybody was done with calibration. So it was kind of a surprise and really no cheating possible, basically, for validation. So everybody had to provide several results, obviously the calibration results for the 141 stations we agreed upon for a 10-year period that was used for calibration. Then we did temporal validation, where the models had to provide results for the same set of stations, but for the last 7 years of that forcing data set. And then the results for the additional stations, once for the calibration time period and once for the validation time period. And then after we were done, that's all streamflow, then we also asked for the additional variables for all the stations. So let's dive a little bit into the highlight results. These are the results of the calibration. So you see 141 stations on the x-axis. It doesn't matter that you can't read the gauge names. What's important, we group them. These are the stations. First are the stations for Lake Superior. Then there's the stations that fall in the Lake Huron watershed, Lake Michigan, Lake Erie, Lake Ontario, and the Ottawa River watershed. On the y-axis, you see the models participating, grouped by being the global model. The global data-driven model is the first one. Then we have all the traditional hydrologic models that are locally calibrated, so at each individual gauge station. And then the last group of models are the ones that have a regional setup. So there's one SWAT model for Lake Superior, one for Lake Huron, and so on. Every single grid cell here basically indicates the performance of a model at one gauge location, and blue means good, red means not so good. On the other side of the y-axis, you can see the median performance, so basically the median overall performances for the individual gauge stations. So what we can see here, just very high level, of course, the LSTMs are like the best model at all in calibration. Then we have the models that are locally calibrated that are kind of better than the ones that are regionally calibrated. That's kind of very known in hydrology, right? That it looks like this. And now if we move on to temporal validation, so we are keeping the calibration stations on the x-axis, but we are using a new period of time where we evaluate the models. We still see that the LSTM, so the data-driven model, is the best, but it's kind of close to several locally calibrated models, while the locally calibrated models are still slightly better than the regionally calibrated models. Again, the details can be found all in the paper, so we dive into why are these stations not working for the regionally calibrated models and so on. So all these details are actually in the preprint. When we now do spatial validation, so we are looking at the 71 surprise gauge stations in the calibration period, we see the same pattern. So we see the data-driven models are significantly better than any of the traditional models. Like there is a huge gap between data-driven and hydrologic or land surface model. Again, there are some stations that don't work, but they also don't work in other models, blah, blah, blah. All those details, again, in the publication. So we really dive into every single gauge station that isn't working well there and try to find some reasons for this. Lastly, the out of sample validation, most interesting, it's the period we never used for calibration and also the stations that we never used for calibration. So again, consistent behavior, data-driven, significantly better than any of the 12 other more traditional process-based models, with a huge gap in between them. So that was kind of surprising because everybody thought like, well, those models will not work in validation, actually. So, but these results show that it's actually not the case. Okay, moving on to streamflow done, moving on to the additional data sets. So we also evaluated AET, soil, surface soil moisture, and snow water equivalent. We use two different ways of comparing those reference data sets with our model outputs to not favor different types of models because some are set up lumped, some are distributed. So we wanted to have a balance between how we compare. So we first compare the models basin-wise and then also per grid cell. We use KGE for AET and SWE, and for surface soil moisture, since surface soil moisture is not represented in most of the models directly, we are only looking at the correlation component of KGE to evaluate the surface soil moisture. Results look, first of all, similar to stream flow. So we are comparing basin-wise. So we aggregate the reference data sets, we aggregate the model outputs to basin scale, and then compare the two time series at all the 212 locations we have for all the models. Please note that the LSTMs are not here anymore because data-driven models, or the data-driven model we used here, can only give us results for the variables that they are actually trained on, and we never trained on snow water equivalent in this case. So they don't provide results, so we are left with the 12 traditional models. So again, this is only to highlight that we have those results. Without going too much into detail, but in the paper we are discussing what these stations, for example, have in common. So now we don't know where these stations are actually physically located, right? So it becomes really interesting to look into the grid cell-wise comparison. So every grid cell of the reference data set is compared to what a model output or a model gave us for this variable. Again, blue means good, so high KGE, and red means not so good KGE. So we can now see spatial patterns when we are comparing like the grid cell-wise model outputs. So interesting results. So for example, the most complex models like Mesh Class, Mesh SVS, and GEM Hydro are working really, really well actually everywhere besides like between Lake Erie and Lake Huron. We dive into the results in the paper. And my last slide is we summarize all those results on the website because it's so much. You can go to hydrohub.org, you will find all those results. You can click and compare every model at each different gauge station with each other, dive into the hydrograph, zoom in, and see what the detailed results actually are. And with that, I'm gonna finish and hope that gave you a good overview.
Thank you much, Julie, for the presentation. So our next presentation will be given by Robin Thorne, and the presentation title is Recommendations to Enhance Hydrological Models for Improved Estimates of Climate Impacts on Northern Waters. So Robin, the floor is yours.
Great. Okay, great. Thanks so much. So changes in the Arctic are having an impact on, let's see my screen here, interaction between surface water, shallow subsurface water, lakes, and stream flow. So up there, permafrost is expected to enhance spatial temporal variability in the active layer thickness, increase occurrence of talics, subsidence, and the contribution of groundwater stream flow, and also increase conductivity. So there's a number of processes that are unique to cold region hydrology. So I'm not going to go through them all, but just know there are some more than just the temperate regions. Hydraulic models themselves are useful tools to investigate how warming and permafrost thaw will influence the cold region processes, evaluate anthropogenic impacts on the processes up there, help inform water resources and management decisions. They have to work with a sparse observational network in such a complex cold region systems. There's some kind of limitation in terms of incorporating a high degree of spatial variability to control the runoff. Interaction between the permafrost, groundwater, and stream flow does need improving, with the models lacking sophisticated permafrost groundwater model components. And it's also kind of limited in dynamics of the soil thermal and soil moisture fluxes, subsidence, and freeze thaw processes. Cryohydrological models model groundwater in cold regions. There's been recent focuses on changes in the active layer thickness, the lateral transfer of energy, groundwater discharge, and even the hydrogeological regime itself. But they're limited in surface processes, particularly snow cover vegetation, and usually applied at a small scale and in ideal environmental conditions. So overall project dealing with is just examine the past hydrological modeling studies conducted within and around the Trail Valley Creek research watershed. From that look at determine like some of the limitations of selected models that were done, make some recommendations to enhance model development, especially for this region, in hopes that, understand the ability of the model interacts between the surface and subsurface hydrology under these thawing permafrost, and to assess a wide range of future hydrologic changes with this changing environment. So Trail Valley Creek itself, just north of Inuvik, covers about 68 square kilometers. located in an ice-rich permafrost region. It does have a sub-basin that we have done a number of studies on, Sisseton Creek. It's got a long-term climate hydrological data available, includes lake monitoring for water level as well as evaporation and discharge. Since the site was established, been an extensive number of research papers, and it's also part of the Northern Water Features study domain. So just for time constraints, just looking at one project here. So back in 2011, Dreezy, so they used a geotop cryo hydrological geological model to understand how topography of the ground surface in Sisseton Creek influences the spatial variability and depth of the active layer. So just basically following some work that was done by Quinton and Marsh. For the modeling, they didn't, for this particular time, didn't cover snow cover or effective vegetation, but they found that the measured and modeled thaw depths did compare reasonably well over the warmer months. And that the spatial patterns of the thaw were controlled mainly by the spatial distribution of soil moisture, which is then determined by the subsurface flow patterns. So looking at their study, some suggestions, recommendations from future work, and actually current work going on right now, it's basically couple the surface hydrological models and use it as an upper boundary condition for the cryohydrogeological model. And also to make sure that it's important to include the small scale processes within the models, especially for these permafrost environments. Another example looked at thermokarst lakes. So lake hydrology up there, influenced by a seasonal preference of ice cover. Arctic is dominated by an immense number of thermokarst lakes susceptible to rapid drainage, which could then be risk to people, infrastructure, and destruction of fish habitat, for example. Past studies have looked at the thermokarst lakes with modeling, and they found that processes associated with the channel development after rapid lake drainage. They also looked at the process leading to initiation of drainage, but were unable to determine any specific causes of the rapid drainage, but showed that the relative importance of the process associated with the drainage will be enhanced with a warming climate. So looking at this future work involves adding a simple lake model module or a process-based lake model to the current models available, as we really need to consider the lake ice symphonology, the evaporation, lake levels, network of coupled lakes, for example, the connectivity between the lakes and the stream flow, and even the fill and spill concepts. For dividing up the watershed, you can do it into units, treated as statistical objects. That's for any analysis simulation. So basically for these permafrost regions, you need to find an ideal small scale approach to deal with the process going on. So it really depends on the key hydrological process of your study, the basic characteristics, the objectives, the data that's actually available, your desired spatial resolution, your computational resources, and the expertise of the user. So for here, ideal model would allow for different spatial scales and over large extents. So for example, like the TIN networks, or the triangulated irregular networks, they're flexible, able to map areas of high heterogeneity, but they can also be useful because they have less points over areas of low relief. So just to wrap it up, so need to provide timely, accurate simulations to help understand the interaction between the surface and the subsurface up there. So as each model has their unique characteristics and limitations, if implementation, other recommendations will help focus on the permafrost thaw at some critical scales and help with analysis of key hydrological processes for this region. So hope that the next generation of these models will help address these challenges in order to evaluate the impacts and predict changes in the cold region hypothesis, and hoping to develop some kind of future mitigation plans. My email is just on the bottom there if anyone wants to contact me with some questions or discussion.
Thank you so much, Robin, for the presentation. I think we may have time for one question. So I see that there is a question in the chat from Ari. Any chance it's open source? So Robin, the question is, oh, I see.
Oh.
So the question was to the previous presentation, I believe, not yours. So if anybody else has a question, we have time for one question. Okay, hearing none. So we'll move on to the next presentation. And the next presentation will be given by myself. And the presentation title is Towards More Effective Representation of the Variable Contributing Area in Hydrologic Models, Model-Specific Approach. So let me share the screen. Okay, I would like to start first with a land acknowledgement. It's always an honor and a pleasure to live, work, and present from the traditional Treaty 7 territory in southern Alberta, the homeland of the Métis Nation, and we always pay our respect to the First Nations and the Métis ancestor of this place. So the map you see on the right-hand side here shows the extents of the non-contributing area, which is also known as the prairie pothole area. A typical landscape within the prairies looks like this. The landscape is dominated by numerous land depressions, which are known as prairie potholes. These potholes have the ability to retain substantial amounts of surface runoff, and therefore the prairie watershed is known to be complex and nonlinear. Also, due to the existence of these numerous land depressions, the prairie region is designated as being non-contributing, wherein most areas do not contribute flow to the outlet. And as you can see from this animated figure, the contributing area is known to be spatially and temporally variable. And the contributing area or the non-contributing area changes based on the state of the depression. This figure, the animated figure here, shows a simulation from the Smith Creek Research Basin. As you can see here, at the beginning of the spring snowmelt period, when the depressions start to receive more input water due to the melt of the snowpack, we can see that the surface area of the depressions start to increase, and many of them start to merge to form larger depressions, as you can see right now. And accordingly, the non-contributing area decreases significantly, or in other words, the contributing area increases significantly. On the other hand, during the summer period, when there is no more input into the depressions and water is being removed out of the system due to either infiltration and or evaporation, the connection between the depressions start to break and they are no longer connected. And therefore, each one of those depressions might be isolated, and accordingly, the non-contributing area changes dramatically. Due to this dynamic connection between the depressions and the non-contributing area, the prairies are typically known as the graveyard of hydrologic models. So currently, or there are current approaches that are used to represent these land depressions in different hydrologic models. And these approaches can be divided into one of these two categories. They can be either conceptual or physical. Conceptual approaches represent these depressions as distinct storage units or storage buckets, and sometimes they lump all of them into a single storage bucket. This kind of approach only generates runoff when the water depth inside the storage unit exceeds its capacity. This approach is computationally and data efficient. However, it might not be accurate and cannot be used to represent the full dynamics of the depressions. On the other hand, more physical approaches have more accurate representation of the dynamics of the non-contributing area and depressional storage. However, such algorithms or such approaches require high resolution input data or high resolution terrain data, and therefore they are computationally and data intensive. Therefore, we are looking for a new computationally and numerically efficient approach that can merge the advantages of both approaches. It can be computationally and data efficient, and more importantly, it can be used accurately to represent the depressional storage dynamics. So our main objective for this study is to improve the representation of the variable contributing area, or in other words, improve the representation of the land depression or prairie pothole representation in different hydrologic models. We used the recently developed hysteretic and gatekeeping depressional model, the HGDM model, to represent the variable contributing area. And we have implemented HGDM in different hydrologic models. However, for this study, I'm going to show you our implementation for the HYPE modeling framework as the first model for this test case. So the HGDM model uses the hysteretic relationship between the volume fraction or the volume of water in the depressions and the contributing fraction of the basin. And the typical hysteretic relationship looks like this. The depression can only, or this figure can consist of two phases, the filling phase and the drying phase. The filling phase happens when the depressions receive input water from the landscape, and the drying happens when the depressions lose water due to evaporation and infiltration. As you can see, during the filling curve, the volume fraction and the contributing area changes accordingly. However, when drying happens out of the depressions, the contributing area drops immediately to zero, regardless of what state the volume fraction is at. So within this study done by Shook et al. 2021, they showed that the relationship for the filling curve can be approximated as a linear relationship. So we can approximate this relationship to be a linear relationship. And this is not only valid for a basin that's very dry or that starts from a zero volume fraction. It can also be applied to any state. Let's say that the volume fraction is around 40% full and depressions are started to be filling from that state, then they will follow a linear relationship until they reach one-on-one in terms of the volume fraction and the contributing fraction. And this linear relationship is valid for any basin, regardless of what spatial distribution of the depressions within the basin. And this is valid for basins that are occupied with numerous land depression, which is the typical case of any prairie basin. So we implemented the HGDM model into the HYPE modeling framework. And HYPE is a semi-distributed and a flexible model, and it has been used to simulate the hydrologic cycle in Canada and for the entire globe. This figure here on the right-hand side shows the schematic representation of the HYPE modeling framework. I'm not going to explain all the details, but the most important thing to note here is that HYPE itself has something called local lake or internal lake module, wherein it aggregates all the local lakes within the basin and lump them into one single storage unit. And then this storage unit only generates runoff when it exceeds its capacity. What we have done here, we have replaced this component, which is faded in here, with HGDM. And in this setup, HGDM receives lateral runoff from the upland area, as well as net vertical fluxes, which is precipitation minus evaporation. In this setup, HGDM calculates the variable contributing area and the outflow from the depressions, and then pass the runoff back into HYPE so that it can be used by subsequent calculation. We have tested the modified HYPE model, which is referred to as HYPE HGDM, versus the HYPE model with its original local lake or HYPE I-Lake model on the Smith Creek Research Basin within the heart of the prairies. So the following is only a sample result. As you can see here, the HYPE I-Lake model or the unmodified HYPE model wasn't able to capture the overall hydrograph nor any of the peak flows during the calibration period, despite of calibrating its parameter to fit the flows. The same poor performance continues during the validation period, and the model wasn't able to capture the overall hydrograph nor none of the peak flows. On the other hand, when we look at the modified HYPE model, the HYPE HGDM, the model was better able to capture the overall hydrograph during the calibration period, and more importantly, showed good estimation of the magnitude of the 2011 flooding event. The same good performance continues in the validation period, and the model was also able to capture the overall hydrograph, and more importantly, was able to capture the accurate magnitude and timing of the 2014 flooding event. It can be seen here clearly that the inclusion of HGDM improves HYPE's ability to capture the prairie stream flow. The same can be concluded when we look at performance measures, the KGE. It can be seen that HYPE HGDM showed better performance in both calibration and validation period when compared to the HYPE model with its original lake module. So in conclusion, and as you have seen from the previous figure, HYPE HGDM outperformed the HYPE model in stream flow simulation. And more importantly, the HYPE HGDM is useful for stream flow prediction, not only in the prairie region, but also across the Arctic region, which is also dominated by the land depressions. And now with the inclusion of HGDM into HYPE, HYPE can now support nutrient transport simulation and tracers across prairie depressions and prairie basins. And this will be very useful for assessing water quantities and qualities across the highly cultivated prairie region. And lastly, efforts are currently being made to make HGDM implementation more model agnostic so that it can be implemented into any other hydrologic modeling framework. Thank you so much. And the following are my contact details in case you need to reach out with any questions. Now we'll move on to the next presentation, which will be given by Kylie Klink. And the presentation title is Using Actors to Increase Scalability and Fault Tolerance of the SUMA Model. So Kylie, the floor is yours.
Thank you. So today I'll be presenting using actors to increase scalability and fault tolerance within SUMA. My name is Kyle Klink, and helping me on this project are Dr. Kevin Green and Dr. Raven Spiteri. We are part of the Numerical Simulations Laboratory at the University of Saskatchewan. So the outline for today's talk, I'll introduce you to what SUMA is and some of the motivation and challenges that we run into with running SUMA at large scales. And then I'll explain kind of what actors are and why we think they're the solution to the problems that we're having. And then I'll show you some results of our implementation of SUMA actors. So SUMA stands for the Structure for Unifying Multiple Modeling Alternatives. It's a flexible process-based hydrological model that allows you to evaluate different model representations all within the same program. It's built on a general set of conservation equations and a common numerical solver. It allows you to simulate the fluxes of water and energy over differing spatial scales. And these differing spatial scales are known as GRUs and HRUs. And a GRU can contain one or more HRUs. So generally when we're running this program, we have thousands of HRUs that we need to run. And we want to batch them up into jobs that we then submit to a supercomputer. And that batching up of processes can be quite cumbersome because they can create pretty convoluted batch scripts to get the most efficient use out of the supercomputer. So as SUMA actors, we aim to fix that. We also aim to fix the fault tolerance of SUMA because another issue that arises is that some of these jobs will fail, and the failures usually are caused by just one HRU, but all the computation is lost. If you're running 500 HRUs and you run into a problem with just one, you lose all that computation for 500. And that means you have to resubmit it into the scheduler and wait for your results after you've diagnosed where that failure actually is. And then all the while, we want to increase the efficient use of computing resources. And then the total goal here is to decrease the amount of human intervention needed to get all jobs to succeed. Because at the end of the day, the user's job is hard and we don't want the programs making their jobs harder. So to do this, we want to use the actor model. And the actor model is a concurrency paradigm where actors are considered the basic unit of concurrency. They consist of a private state and they communicate only by messages. So when a message is received, an actor can execute actions on its own state, message other actors, respond other actors. So if we kind of look at the actor system here to the right, we can see that actors contain a state, some methods that can manipulate that state, some methods that can create other actors, or some methods that can message other actors. So an actor will receive a message, it will parse its mailbox, and that message will invoke one of those methods that manipulates state, create actors, or sends messages. So how does this look in practice? Well, spawning actors is computationally cheap. So if we compare it to MPI, MPI processes, or for MPI, they generally recommend that you spawn as many MPI processes as you have CPUs. But with actors, this is not the case. We can spawn thousands of actors, no problem, no matter what the CPU is doing. So what we want to do with our programs is conceptualize them as state components, conceptualize the state components as actors in our programs that can communicate by sending each other messages. And what this does, and we want this to be done asynchronously so that we're always using the CPU. So what we do in SUMA actors is that we implement the HRU component as its own actor. And now this is the main component that carries out the simulation, and they're independent of each other and can be run concurrently. So we can create as many HRU actors as needed, and the number of CPUs is not relevant because now when a CPU becomes available, an HRU actor can run on it. So why do we want to use actors? Well, they're very scalable, and they also increase the efficiency of the CPU, and we have fewer idle CPUs. And more importantly, we want to increase the fault tolerance because now we have these isolated tasks that when failures do happen, that we can allow the rest of the computation to continue. But we do take it one step further because we implement actors, what is known as actor supervision. So when you spawn actors, actors will create a parent-child relationship. So the HRU can consider the child actor. And what we do in SUMA actors is that when that HRU fails, its parent actor will then respawn it with a new parameter set that's more likely to succeed. So what we're trying to achieve here is a more flexible and adaptable program that can make decisions during runtime and decrease the amount of human intervention needed to resubmit those jobs. So just to show you how scalable actors really are, we ran 4 separate tests on 4 separate batches of 500 HRUs. using various CPU counts. And as plotted by the black line, you can see that this is known as perfect scaling. And you can see that our results are in line with perfect scaling. So what we're seeing here is that as we double the CPU, we're having the wall clock time, and this is known as strong scaling. And this is what we want to see. So, but how does our implementation of SUMA actors compare with the original version of SUMA? Well, we compared it running against the North American domain, which consists of over 500,000 HRUs. So what we have to do is we have to batch those HRUs into jobs of about 1,000, and we submit those jobs with 8 CPUs per job. For SUMA original, we need to further batch into as many subtasks as cores. So that's a little bit more work on the user's end to create that bash script that gets that right. Whereas the SUMA actors just needs to know how many cores it's assigned and how many HRUs it's computing, and you just submit it. There's no need to subtask here. So if we look at the results, we have 2 histograms here. We'll start with the one on the left, which is the wall clock time. What we can see here is that the results of the 2 programs are comparable, but when we get down to it, SUMA original is highlighted in yellow, and we can see that the graph here skews to the left. So that means more jobs are finishing in less time here. But this is to be expected because at the end of the day, both programs are doing the same amount of work, and SUMA actors does have some extra overhead. But what we're trying to do here is provide the convenience of having more work being done, because what we observe in the North American domain is that there's 3 failures, and they happen in different batches, so that with SUMA original, you will have to resubmit those batches, wait in the queue, and then wait for those results, which takes a couple hours. But with SUMA actors, once you get back to your results, all the results will be there. So now on the flip side, if we look at CPU efficiency, we can see that SUMA actors has very little idle CPU in most of its jobs, which is something that the organizations such as Compute Canada like to see, because when you check out the resources, they want to make sure that they're being used to the fullest extent. Otherwise, they would have preferred someone else to use those resources. So what do we achieve with SUMA actors here? Well, we're aiming at creating a general framework that uses actors to reduce future failures and human intervention in the resubmission process. So we're trying to bake in this resubmission process into the program so that you just have to invoke the program once. You don't have to go back the next day and figure out what went wrong. So we do have this general conditional now that we're aiming to always have to hit this else condition where we're doing the automatic resolution, but we don't live in a perfect world, and the program is still being developed that when an HRU does run into an error, it will stop and let the rest of them continue. But the programmer will then need to figure out how to automatically handle this and then implement the new error handling. But after that, future data sets should not encounter this error, which saves the user time and provides the user with more successful results. At the end of the day, we're also showing that actors can be used with Fortran, even though Fortran doesn't have an explicit actors library, which we think is a pretty cool thing. So thank you for having me, and your contact information is on the screen.
Thanks, Kyle, for the presentation. So we have time for one question. So feel free to unmute yourself and ask questions if you have. Okay, so now we move on to the next presentation. And our next presentation will be given by Matthew Young. And the title of the presentation is Integration of Text and Geospatial Search for Hydrographic Dataset using the Lucene Search Library. So Matthew, the floor is yours.
Hello, everybody. Sorry, I was muted. Can you guys see my screen?
Yes.
Okay. Hello, everybody. I'm an undergrad student from the University of Waterloo working with Professor Jimmy Lin. And today I present to you the integration of text and geospatial search for hydrographic data sets using the Lucene Search Library. So to begin, let me talk about the motivation behind our work. So you might already be familiar with the proprietary ArcGIS family of software packages. And there's also the more recent QGIS, a non-proprietary alternative you might also know already. So they are both standalone applications that support a wide range of geospatial analytics tasks. So now let me draw your attention to an entirely different field, artificial intelligence, or AI. So in recent years, AI techniques have permeated all aspects of data analytics, and that includes geospatial analytics. However, it is difficult to integrate AI into the platforms that we just mentioned because they are standalone applications. They have their own set of tools and interfaces, and that lack of flexibility prevents easy integration. Furthermore, it is also difficult to integrate ArcGIS and QGIS with external data sources due to restrictions on data format. So these existing bottlenecks of integration are the motivation behind our research. Eventually, we would like to integrate AI and data with geospatial analytics. And this project is the starting point to accomplish just that. Specifically, this project lies at the intersection of natural language processing, or NLP, information retrieval, or IR, and geospatial analytics. NLP and IR are heavily tied to AI nowadays because deep learning and neural networks dominate modern NLP and IR techniques. And again, existing GIS systems do not provide support for these new AI-related advancements because they are standalone applications that just aren't flexible enough. So just before I talk about the actual application, let me introduce to you two data sets. So first off, we have Wikidata, which provides a mapping between the river names to the actual river entities, each river entity containing the metadata of the given river, including geographic coordinates of the river's source and mouths, as shown on the right here. We also have another data set, Hydrosheds, which provides the vectorized line network of the rivers and basin geometries. You can see the river and basin geometries that belong to the Hydrosheds database on the right over here. So we have these two data sets, Wikidata, which has the rivers associated with their names, and Hydrosheds, which has the rivers associated with their geometries. Wouldn't it be great if we can piece the two together and associate the names with the geometries? And our application does exactly that. It is an example of integrating AI and data with geospatial analytics. So this is a screenshot taken from our application. So as you can see on the top left here, there's a search box that takes in a river name. Once you press enter, our application computes the matching rivers. So in this case, Fraser River, along with the geometry of the river, outlined in dark green, and as well as the drainage basin outlined in light blue. So next up, I'll be talking about the architecture of the application. I'll be splitting the architecture into several components: text search, geo search, the web interface, and how we integrate everything together. So to begin, let me talk about the text search component. The text search component takes in the river name as its query, and it returns the mouth and source coordinates of the river retrieved from Wikidata as the search result. We do this search through our group's Answerini and Peizerini toolkits, which use the Lucene search library under the hood. And let me just give you a briefing on that. Lucene is an open source search library that allows us to do both text and geospatial search. And Answerini and Peizerini are toolkits that our group maintains, which allow developers to access Lucene more easily. So using Answerini and Peizerini, we're able to build a Lucene index on the Wikidata, and this index allows Lucene to search efficiently on Wikidata. Next up, let me talk about the geospatial search component. So for geospatial search, the query is a coordinate, and the search result is the closest river segment or basin to that coordinate. So the actual search process is actually very similar to text search, because instead of Wikidata, we now just search on Hydrosheds, the Hydrosheds data set instead. So for this project, we actually added Lucene's geospatial search feature to the code bases that our group maintains, Answerini and Peizerini, and we build our index and search all through Lucene. Now let me talk about the web interface, which is what you saw the screenshot in one of the previous slides. So our website is built on React, Leaflet, and Flask. So React is a popular framework for building how a website looks, and Leaflet is the standard approach to rendering maps as well as shapes on maps. So the river and basin that were traced out were done through React and Leaflet. And Flask is for sending the text Fraser River into the text box to our backend search engine. Finally, let me show you how we integrate everything together. To that end, I'll answer the question. So what happens when we press enter on the search box? So once we've pressed enter on the search box, the words Fraser River is delivered through Flask to our backend. And the first thing our backend does is to do a text search on Wikidata on those words through Lucene. And through text search, as we mentioned before, we can get the source and mouth coordinates of the river retrieved through Wikidata. And through those mouth and source coordinates of the river, we can do a geospatial search on those coordinates and find the closest basins to the mouth and source coordinates of the river. And let's call these basins the mouth and source basins. So now with these basins, we would like to find the entire river and its basin, drainage basin, just like shown out on the screenshot. So how do we do that? So for finding the river geometries, we start from the source basin and trace downstream to the mouth. So we start from the source basin shown here, and then each river reach within this trace, as you can see here, we slowly trace down, and each river reach within this trace is returned as the river, and shown by the dark green lines in this case in the search of the Fraser River. So for finding the drainage basin geometries, we start at the mouth basin to do a breadth first search. So yeah, we start at the mouth basin and we ask which basins have this mouth basin as a downstream basin. So these three basins, for each of those basins, as shown by the three arrows, we ask the same question again: which basins have each of these basins as a downstream basin? And we continue this process until there's no more basins that satisfies this answer, and everything we found is returned as our drainage basin, shown by the light blue lines. So some of the next steps include replacing the current text search through Lucene with more advanced text search using deep learning and neural networks. And that would actually be easy because our group's Pizzarini already supports the state-of-the-art AI text search. And also to increase the speed of our application and accuracy of rivers with incomplete data. For example, if we don't have a source or mouth coordinate in Wikidata, is also on our bucket list. So yeah, that's it for our application. Do you guys have any questions? Or I'm not sure if I have time for any questions.
Thanks, Matt, for the presentation. I think we have time for one question.
Hi, Matthew, this is Julie. Thanks so much for that talk. That was really interesting. I have a quick question. What's like the average response time for requests? So if I look for Grand River, like how long does it take? Is it like instantaneous or is it like taking a second?
So yeah, it depends on the number of results we return. So I think the traversal time for only the Grand River currently is about, I think it's just under 10 seconds roughly. Yeah.
Okay, cool. Thank you so much.
Yeah.
Thanks, Matthew. So our next presentation will be given by Hongren Shan, and the title of the presentation is Time to Update the Split Sample Approach to Hydrological Model Calibration.
Yeah,
so
thanks, Mohammed. Let me share my screen. Can you see my screen now, Mohammed?
Yes. Yeah, but we cannot see the presentation. Yeah,
the slide is here. Okay. Okay, I'll start. Hello, everybody. I'm Hongren. My talk today is entitled Time to Update the Split Sample Approach in Hydrological Model Calibration. This work was collaborated with Dr. Brian Towson and Dr. Julie Mai. So this presentation is a mirror of our paper published on WRR recently. I will take one of the three key analyses reported in that paper as an example to show you the contributions we made. So first, we proposed the research question that for continuous streamflow prediction, how should we modelers split the historical data between calibration and the validation? There could be many choices. For example, how should we choose between newer data and older data, between a long and a short record, and more adventurous? Can we calibrate it to all data and ignore validating the model? So we answered these questions in the study. And firstly, I want to show you what we finally found out. So two main recommendations. One is skipping the temporal validation entirely and calibrating to all available data you have. The other one is don't calibrate it to the older data and then validate to the newer data. This is an inferior choice, and we should avoid in future modeling practice. And you might be skeptical, but now let me convince you to show you what we did to get there. So first, a light background about the split sample test, SST. This is a method, has been a paradigm in hydrological modeling for half centuries, and we have been used to calibrate our models and then validate them. But a few studies suggested that using full period could be preferred. But as one of the limitations of the SST method, calibration selection is an ambiguous problem. Some studies reported 96% of the sample literature use older data for calibration and newer data for validation. And these studies are generally based on limited catchment, which could be case specific. So let's talk about the methodology. Assume we are building our models at time now, and we have historical data available, and we want to do something such as forecasting and prediction in the future period. Generally, the SST method tells us to split the historical data to calibrate and validate the model to identify the parameters and then extrapolate models to the future period. And our goal in this work is to investigate which calibration validation splitting scheme would be better in the future time. And in this study, we call this the testing period. And testing period is different with validation. So it is not a prediction or indication of how well the model might do in operation. It is how well the model actually does in operation. And because it always follows the time we build our models, and hence we are using this testing period to mimic the future period our models will be extrapolated to. And in this experiment, we are aiming at assessing different split sample decisions. This is why we need a testing period to mimic the future. While in the most model cases, we don't need this testing period. We only need to decide which data splitting schemes we want to use for your model building, and then build your models in the historical period and then apply to the future time period. So this is here is a case. So first, for the record, I want to mention that we are doing investigations for temporal calibration and validation in this work. And the x-axis in this figure is the time. The y-axis is the possible data splitting schemes. Suppose we build our models on January 1st, 2010, and then deploy it operationally, and waiting 5 years, how did the model do in operations? So these 5 years here, colored as red, are the future time compared to the 2010 when we build our model. And there's a testing period we call in this work. So when we build our models on January 1st, 2010, we have 30 years of data to build our model. And we propose 10 different splitting schemes between calibration and validation. So we can see that these schemes, which we call calibration subperiod CSPs, they have different lengths, such as 30% of the available data, 50%, 70%, and 100%, which is the full period. And these CSPs also cover different parts in the historical period, from the older years to the most recent years. And this is not enough. We further roll back the model build years to 4 more cases. And here, in total, we have 5 different model build years, each having 10 different CSPs. Different model build years give us different scenarios of data availabilities in model building, and also reduces the impacts of climate variability on conclusion drawn. And still, this is not the end. In this unique experiment, we apply our models to various testing periods. We used 3 different testing scenarios for each testing period. So the first 3 testing periods, the first 5 years of the testing period, and the entire testing period. And this allows us to test our models in a wide range of scenarios And in total, there are 14 different testing scenarios across these 5 subplots. And we selected 463 catchments out of the CAMELS data set, and each having good quality and long-term metaforcings and streamflow data. And we used GR4J and HMAT in this work. Both were emulated in the Raven hydrological modeling framework. And we calibrated our models using the DDS algorithm, and the calibration and the evaluation metric is KGE. And we performed 20 optimizations for each model calibration. And in total, we performed a near 1 million model calibration experiment in this study. And this large sample result will give us statistical meaningful evidence on our research question. And so think about the purpose of doing a calibration and a validation. It is to classify models as adequate or inadequate for model application period. If a model is inadequate, we should not use it for future water management decision making. And in this work, we used reference flow to benchmark the lowest KGE level that a good model should be beat. And the reference flow is further formalized as the reference KGE. So reference to KGE here is purely observation data based. And once you have an observed stream flow record, we can derive this reference KGE. And any model failed in this calibration and validation experiment will trigger a decision to discard the calibrated model. And instead we use reference flow for testing period. And now we compare the quality of the split sample decisions. So we consider it a multi-objective decision-making problem. And so we have 2 objectives. First is to maximize the median KGE, and the second is to maximize the model classification accuracy. And this classification accuracy is the frequency that a CSP choice correctly classifies model testing failures and the success. And here we defined the classification accuracy in the confusion matrix framework. And based on the model calibration and validation results, we can classify the testing outcomes into 4 categories. In this table, the green categories means our CSP decisions are correct, which are preferred. And we derived the 2 metrics. One is the accuracy, which is the fraction of the CSP correctly working. And we used the 1 minus accuracy to define the error rate. So we hope the accuracy would be larger and the error rate would be smaller. So back into the 2 objectives, we employed the Pareto front to help us to look into the optimal CSP. So in this figure, different colors denote different recentness of a CSP. The red circles are recent scores with 100%, meaning the most recent data are used. And recency score with 30 means the data are pretty old. And for the median KG versus accuracy, the upper right corner will be the optimal solution. And in this case, we see that the full period CSP fall onto the Pareto front. And the error rate versus the median KGE, it's clear that some older and short period CSPs have twice errors than the full period CSP. And this is actually what we hypothesized in the beginning of this study. And now we can plot all the trade-offs for 2 models and 5 model builders. And in this figure, we can easily identify those full period CSPs marked as white stars are most lying in the lower right corner. And 9 in 10 of them are falling into the Pareto front, which make them non-dominated solutions. As I mentioned before, many studies tend to use older data to calibrate model and newer data for validation. But in this figure, we can see those older CSPs, which is in blue and the gray circles. They are really worse than the red stars, the full period CSPs, and the most recent CSPs in red circles.
Sorry, I'm going to interrupt you, but you have exceeded the time. So if you could please wrap up.
I will run quickly. Yeah. So we summarized the 3 testing periods results in this table. And we can see that the 4 period CSPs show a very strong evidence that it's preferable than the other CSPs in this multi-objective analysis. And I recall the recommendations I mentioned before. We recommend using the 4 period for calibration, and if you must validate your model, use the newer data for calibrate and validate the older data. Okay, I'll stop here. Thanks.
Thank you, Hongren, for the presentation. So now we'll move on to the lightning talk. And the first lightning talk will be given by Lauren Borke, and under the title of Drivers of Hydrological Response for Distinct Wetland Complexes in a High Latitude Alpine Watershed.
I just need you to stop. Thanks. Okay.
Yep.
Perfect. Great. Hi, everyone. My name is Lauren, and I'm a master's student at McMaster University with Dr. Sean Carey. So wetlands play an important part in the hydrology in high latitude regions. They store large amounts of water, which can help to sustain these areas throughout the summer season after initial snowmelts. In Wolf Creek Research Basin, an alpine area underlain by discontinuous permafrost located near Whitehorse, Yukon, wetlands are abundant but poorly mapped. No formal study has been completed to determine the role of these wetlands, their heterogeneity, and how landscape position will impact their response to precipitation. The goal of this study was to compare the hydrological response of 2 distinct wetland types in Wolf Creek, a wetland perched high in the landscape and a valley bottom wetland. We installed a series of well nests at each of these sites, and surface water samples of stable water isotopes were taken weekly. Both wetlands responded differently to precipitation events. In the perch wetlands, during the largest rain event, the wells responded between 20 to 40 centimeters, while the response in the valley bottom was variable with a maximum response of only 6 centimeters. These valley bottom wetlands remain connected to the landscape through channels, but are also supplied with water from the adjacent house slopes. This connection allowed for the open water ponds to remain wet throughout the season, while the perch wetland was more sensitive to the absolute volume of rain events. Stable isotopes of hydrogen and oxygen in the perch wetland had the largest deviation from a local meteoric waterline compared to that of the valley bottom wetland. At the valley bottom wetlands, even though these areas may experience high rates of evaporation, we don't see the same trend, as the waters are supplied with snowmelt from the hill slopes later into the season compared to those of the perched wetland. The heterogeneity of these wetlands impacts the water table dynamics and their responses to events after snowmelt. Alpine wetland areas will continue to play an important role in the future as permafrost areas change. Changes in wetland storage may occur, which could impact water loss throughout the summer season. Thank you.
Thank you so much. So now we'll move on to the next talk. It will be given by Huya Yin. And the title is The Influence of Weather Seasonality on Well Vulnerability in Cold Regions.
Hi guys. My name is Hao Yin. So I'm a master's student at the University of Waterloo. So my research focuses on weather seasonalities in northern Canada and its impacts to the well vulnerability. So well vulnerability can be analyzed to understand the impacts of human activities to regional groundwater security. So this is important for places where heavily rely on groundwater as their freshwater resource. And a key component of well vulnerability assessment is to simulate the capture zones. However, for regions in northern Canada, simulating capture zones is different because the northern Canada has intensive weather seasonality, and it will cause strong recharge rate variation between summer seasons and winter seasons. And also it will cause flooding hazard. And these aspects need to be considered while delineating capture zones. So in order to evaluate impacts of weather seasonality, we pick up a site called Carmex to do our research. And Carmex is a community that locates at central Yukon. So we will use a fully integrated groundwater model called Hydrogeosphere to build a 3-dimensional groundwater flow model and to simulate the capture zones. So the model will include 3 different scenarios to analyze the impacts of weather seasonalities and the flooding hazard to the capture zone's shape and orientation. And also we will then develop a vulnerability assessment approach that's specifically designed for Northern Canada. And so far, we have got some initial results and they have been added to the poster. Please take a look at the poster if you are interested in our study. Thank you for listening.
Thank you so much. The next talk will be given by Leila Latifovic under the title of The Impact of Gypsy Moth Defoliation Events on Net Ecosystem Productivity in a Mature Deciduous Forest in Southern Ontario.
Thank you so much. Hi, everyone. My name is Leila Latifovic. I'm with McMaster University. I just want to make sure you can see my screen. Can you give me a thumbs up?
Yes, we can see.
Okay, great. I didn't see the green border. So, okay, I'll continue. So my name is Leila Latifovic. I'm with McMaster University. I'm working with Dr. Altaf Arain in the Hydrometeorology and Climatology Lab. My research is examining climate, extreme weather events, and natural disturbance impacts on carbon dynamics of temperate forests. I'm specifically exploring how a gypsy moth defoliation event during the growing season in 2021 impacted carbon sink and source strength of a temperate deciduous forest. The forest is located near Turkey Point and Long Point Provincial Parks, just north of Lake Erie in Southern Ontario. It's a naturally regenerated deciduous forest greater than 90 years of age and is known as CATPD site in the Global Water Futures and Global FluxNet networks. The dominant overstory tree species at TPD is white oak. There are a few scattered conifer species, less than 10%. Results are derived from continuous half-hourly closed path eddy covariance measurements of carbon dioxide, energy, and water vapor exchanges. Simultaneously, meteorological measurements were collected. Some preliminary data analysis and plotting of the carbon flux at TPD shows the severe impact the gypsy moth had on productivity. The forest was a source of carbon in 2021. In table 1, we review seasonal values of carbon fluxes. If I can draw your attention to the last 2 columns for a comparison of 2021, the year of the defoliation disturbance, and the previous 5-year mean, we can see the severe impact the defoliation event had on NEP. Pre-defoliation average annual NEP was 187 grams of carbon per meter squared per year. While following the disturbance, NEP was negative 455 grams of carbon per meter squared. So quite a significant change. Photosynthesis naturally dropped as illustrated by lower GP values that you can see at the top of the slide, while respiration increased. Figure 1 is a clear illustrative example of the deviation in the carbon flux in 2021. Months of the year are plotted on the x-axis and carbon fluxes on the y-axis with different colored lines representing different years. We can see that 2021, the fuchsia line deviated significantly from what would have been expected during the growing season, resulting in the forest becoming a significant source of carbon. I'd love to discuss more over my poster. Please be sure to visit me tomorrow. Thank you so much.
Thank you. The next talk will be given by Brampton Duncan, and the presentation title is The Drying of the Arctic and Active Layer Development, a case study from the Western Canadian Arctic.
Hello, can you hear me?
Yes, we can hear you and we can see your screen.
All right. So hello, everyone. My name is Brampton Dakin, and I'm an MSc student in Earth Science in conjunction with the Collaborative Water Program at the University of Waterloo. So as the Arctic climate warms, there have been observed changes in snowfall and rainfall, as well as changing evaporation, deepening of the active layer, changes in soil water storage, and changes in slope runoff. These combine to impact stream flow and runoff in poorly understood ways. My graduate degree investigates how water moves in a small Arctic basin and how active layer thaw is changed by this movement during a dry and warm summer. The summer of 2021 was one of the driest and warmest summers on record, with the 7th warmest overall summer and driest July in Nunavik. This research presents a unique opportunity to study the effects of the drying of the Arctic, as it's relatively unknown, and there's a glaring lack of data available during dry summers. It's a phenomenon that's projected to become more common because of global warming, but it's a process that's poorly understood and poorly funded, despite Arctic ecosystems being highly susceptible to change. Many previous studies have overlooked the importance of complex microtopographies, such as hummocks, and the influence that they may have on thaw and groundwater flow, or have only moderately tried to incorporate them. There are two essential components to my research: the field portion and the modeling portion. Field data was collected in Sigsay Creek from May 25th to August 29th, and can be found roughly 50 kilometers north of Nunavik in the Northwest Territories. Data collected included weekly frost table measurements, soil pits, water table depths, and peat thickness studies across the catchment. Using the physically based hydrology permafrost model GeoTop, this research aims to explore the importance of certain processes, such as the amount of snow at freshet, peat thickness, and vegetation that control active layer depths, as well as how the flow of water when accounting for microtopography influences. This research pushes the boundaries of Arctic hydrology and hydrogeology on a few fronts: the issue of including complex microtopographies in modeling efforts, as well as the problem of scale, while also exploring what both warm and dry conditions mean for active layer development and permafrost thaw. It adds a much needed data set covering the drying phenomena, and it seeks answers to the questions that Northern residents are asking, i.e., what will happen to the ground under their feet in the face of global warming. Thank you for your time.
Thank you. So the next talk will be given by Jason Paul on mapping thermokarst land systems.
Give me a second.
Sure.
All right. Hello, I'm Jason Paul, a research assistant with Wilfrid Laurier University. Our poster presents the Northwest Territories Thermokarst Mapping Collective Project and some preliminary results. The project was initiated by the NWT Geological Survey and partners to develop an observation-based data set of thermokarst indicators across the territory. Trained mappers across Canada and the NWT use Sentinel imagery and a GIS-based data model to assess the relative abundance of thermokarst features on a 7.5 by 7.5 kilometer grid system covering the entire NWT. Understanding how permafrost thaw and the diversity of impacts will manifest spatially remains a significant knowledge gap in Arctic change science and a primary goal of this project. Inventory grid cells affected by retrogressive thaw slumping, a common form of thaw-driven mass wasting in the Western Arctic, corresponded well with published fine-scale data sets indicated by the project data on plate A compared with independently published data on plates B and C. Circumpolar and national scale data products aim to depict landscape susceptibility to slope thermokarst and the potential of relics ground ice, contrast our project outputs, and demonstrate the scientific and societal need for empirically based broad-scale data sets evaluating thermokarst characteristics. To examine thermokarst variability in permafrost landscapes, the occurrence of 30 thermokarst features in sampled grid cells across a diverse range of ecoregions from across the NWT were analyzed in a principal coordinates analysis. Map cells largely separated by latitude along the first principal axis, and several thermokarst features associated with differences in permafrost, ground ice, and physiography emerged as important drivers of variation both between and within ecoregions. These data and analyses illustrate the inherent diversity in thermokarst landscapes, indicating landscape variability in thaw-driven trajectories of change and in associated environmental, carbon, and societal consequences. Please come check out our poster if you'd like to learn more, and we'd love to hear from you. Thanks.
Thank you. Our next talk will be given by Ariel Lizogorski on a detailed look at phosphorus accumulation in a 12-year-old multi-cell bioretention system using sequential extractions.
Hi, everyone can see and hear my, oh no, I did not share my screen. Now you share my screen. Awesome, everyone can see and hear me? Yes, thumbs up?
Yes.
Awesome. So bioretention cells are a type of urban stormwater infrastructure that has been favorably shown to reduce and delay volume
of water input to storm drains. But what happens with the pollutants associated with that volume has often resulted in inconsistent results. For example, when it comes to phosphorus, my pollutant of interest, at least part of them might be actually explained by how phosphorus is measured and reported, we found. And to more comprehensively measure phosphorus to get these results, it took a technique that takes more weeks in the laboratory than I have minutes to tell you about what we found out with it. But what did we find? So first of all, we found two things. We found that total phosphorus, that one of the parameters typically measured, accumulated in the soil. You'd be surprised by how novel such a simple statement might be, but as previously mentioned, true field studies on biosystems this age are not very frequent, and their results, when available, are inconsistent. But why the results are inconsistent, and that's where kind of our truly novel results get. That's that bottom figure. And they match previous speculation about why this might be, but there was never confirmation seen in field results before. What we found was that there's two clusters that are linked to total variation in total phosphorus, but critically one that is not. So iron and manganese, a redox-associated system, and an organic carbon-associated system are the ones that were primary to explaining it. And notably, calcium didn't even relate to the phosphorus and calcium minerals nor total phosphorus. So there was like this doubly lack of relationship there. And why is this important? It's because, again, the measurement is done in terms of usually two pools and not all four. And when people are trying to model it, there are a lot of these hidden variables that are at play. And what we've done is we've identified a clear distinction between these that merits further investigation and will drive better modeling in the future. It'll also give us a better idea of impact assessments, flooding, and maintenance and design of these systems, given the fact that they're previously designed around this hidden variable. If you want to learn more, please come and visit me or see the poster later.
Thank you. The next talk will be given by Zhen Tong on the assessment of groundwater flow significance in hydrologic models.
Hi, can Ari stop sharing his screen because I can't share screen while he's doing that.
You can share now.
Yeah. Awesome. Can everyone see my screen?
Yes.
Okay. So good afternoon, everyone. So today I'm going to talk about our study on assessment of groundwater flow significance in hydrological model. So our study site is located at Alder Creek watershed. So our study is mainly trying to examine the significance of shallow, deep groundwater flow on surface water flow prediction through the hydrogeosphere, which is a fully integrated hydrological model, and also the river model as a representative as the surface water model. So for the HGS model, we have developed 5 different models while increasingly complexity to represent the subsurface. So here's all the data that incorporated into the 5 HGS model. For example, the land use type, the 4 different soil type, and also the geological model, which we used based on the data from Hydrology Tier 3 assessment free flow model. So here's the figure to showing the comparison of estimated discharge in summer and winter for all 5 HGS model and observed discharge at one of our gauging stations. And we find that the model with most detailed representation of the subsurface yields the best result and fit best with the observed discharge and better capture the peaks and also the base flow. And we also compared HGS model with the river model, which is a HRU-based surface water model. So it discretized the Alder Creek watershed into over 900 HRUs and used the same input data with the HGS model. So compare with the HGS model and the river model, we find that the overall estimated discharge of HGS model 5 is larger than the river model, while the HGS model 5 is more capturing all the fluctuations and the peaks of the discharge at the New Dundee station, while the river model seems to be more consistent with the base flow. So here are some main conclusions from our study. We find that the model with different subsurface representation yields dramatically different results. And then the one with most detailed representation of the subsurface hydrostratigraphy always yields the most realistic, reliable, and accurate stream flow prediction. So we think that to treat the subsurface more accurately can lead to improved subsurface water distribution and the hydrograph. So if you are interested in our research and topic, please visit us tomorrow in our poster section. Thank you.
Thank you so much. So the next talk will be given by myself on the multimodal intercomparison project on the Saskatchewan-Nelson Churchill River Basin, the Nelson MIP project. So, okay, so hydrologic models have been developed and used for many decades to predict the different components of the hydrologic cycle, as well as to be used to predict various risks to communities such as floods and droughts. However, running these models on large-scale domains with numerous managed and unmanaged lake systems might be problematic. A good example of research or a good example of a test basin or a watershed that's large scale and includes numerous regulated and unregulated lakes is the Nelson Churchill River Basin in North America. As you can see from this figure here, the Nelson Churchill River Basin has an area of about 1.4 million kilometers square, and it includes various topography and various ecozones. It includes the mountain region, as well as wetland and forest region, and more importantly and the more complex prairie region. More importantly, this area hasn't drawn much attention with regard to testing multiple models or doing intercomparison projects, especially or more importantly due to its complex nature. Due to that, we have been working collaboratively and closely with tens of researchers across Canada under the Nelson MIP umbrella, and so that we can build, test, and evaluate the performance of the different hydrologic models. We were able to test and evaluate the performance of 8 hydrologic models on the Nelson Churchill River Basin, and we were able to test their performance with regard to stream flow simulation as well as other hydrologic signatures. And lastly, we were able to come up with certain conclusions and certain outcomes, such that we were able to identify a set of models that have better representation and better simulation of the stream flow across that complex river basin. And more importantly, we were able to identify areas for future model structural improvements. If you would like to know more about this work, please check the Nelson MIP poster. Thank you so much. The last talk will be given by Nastran Saberi on the uncertainty estimations of mapping lake ice using random forest on modest TOA reflectance data.
Hello, everyone. Bear with me just 1 second. Okay, so thank you so much for standing by. This is Nastran Saberi, and I would like to have your attention to my research at GWF as a core modeler affiliated to University of Waterloo. My work would be interesting for researchers who are interested in understanding uncertainties associated to models and data sets, specifically ones that are using machine learning and deep learning methods. Presented work has been built up on previous research at GWF with my colleagues, Professor Duguay and Professor Scott, where we mapped aleatoric uncertainties coming from the data sources in mapping lake ice from radar-sat observations while using CNN's convolutional neural network on Lake Erie. And in this research, we are going beyond calculating uncertainties as a result of using only input data with errors associated to the data sets. We are going beyond this, so we are using a more sophisticated approach on mapping total uncertainties. The uncertainties coming from the model, epistemic uncertainties, and the uncertainties coming from the data source, aleatoric uncertainties. We use this for mapping lake ice, cloud, and water pixels using MODIS data, remotely sensed observations. and more specifically top of atmospheric MODIS data, different bands, and also random forest classifier in an operational mode for producing uncertainty flags for daily lake ice generated by Climate Change Initiative, CCI+, which then it is part of the lake project in ESA, European Space Agency, and now the data set, the study area is on Lake Erie, but of course for the operational mode it will be expanded globally. So a little brief quick background of the core model. As random forest is an ensemble-based approximation, it allows learning different hypotheses, different trees, and then as a result, it gives different expected outcome. And then total uncertainty in a prediction can be calculated by the Shannon entropy of the predicted posterior distribution, whereas calculating the entropy of each probability gives us aleatoric uncertainty, and then epistemic will be total minus aleatoric uncertainty. I will wrap it up, or do you have a question? Okay, sure, just one. Okay, and to sum up, quantifying predictive uncertainty estimates expand product usability, making researchers aware of aleatoric and epistemic uncertainties when incorporating ice fractions in the physical and numerical retrieval models in the form of direct integration of the observation error variance as a quality control flag. That was it. Thank you.
Thank you so much. So that's it for this session. I would like to thank all of you for attending this session. And of course, a special thank you goes to the presenters for their efforts and their great work. Please don't forget to check the dedicated poster session on Wednesday to discuss the posters. Thank you and have a good rest of your day.